In the introductory video to neural networks, I explained how deep learning fits into the overall scheme of artificial intelligence. And I explained that artificial intelligence was just a more general term to describe, technologies where computers do things that appear to be intelligent. Um, Machine learning was one of the enabling technologies of artificial intelligence, and machine learning, at least the supervised case of machine learning, works where we provide the computer sampled, labeled samples, and it learns patterns based on what the examples that we give it. And so, for example, we looked at the image classification task where we said this is a cat, this is not a cat, and it learns how to identify a cat. And I said that so neural networks was really just an extension of machine learning that resulted in large leaps in accuracy. Um, you know, Improvements in accuracy to the extent that things that were not really useful anymore, such as not really useful as they were, such as machine translation, speech recognition, and object recognition. Um, these improvements in accuracy meant that they were finally commercially viable, and so that was thanks to neural networks. So deep learning is really just the use of neural networks that are very large and very complicated with lots of connections. Okay. So these are sort of like subheadings underneath each other. And so this is the name of our unit this week, but that's how it fits into the overall scheme of things. Okay, so with I explained last time that a neural network is, itself an extension of what we do when we're doing regression. Okay, so with regression, we're trying to predict some kind of outcome. We're trying to predict an output variable by doing a weighted sum of the input variables. Okay, and so I showed that we can think of it this way, where the intercept is just this. So we're multiplying the intercept by 1 and then adding this weight times that input variable, this weight times that input variable, this weight times that input variable, and then adding them all up. And so this weighted sum is, just a regular regression. We can optionally pass that output through some kind of function, as we do in the case of logistic regression, and then we can convert this into a log odds, which we can then convert into a probability. Okay, and so I said that so this really is just a way of visualizing regression. But if we take a bunch of these and hook them up together, then we wind up with a neural network. Okay, and the example that I showed. So again, this is just machine learning. So we start off with data, of course, and we have here a data set of churn, right? So this column here is our outcome that we would like to learn how to predict. So 1 means that the customer has churned, they've left the service. 0 means they haven't. And so we would like to build a predictive model that will allow us to enter in, new data, so calls and years for some customer, and then be able to predict whether they will churn or not. Okay, and so I showed how when we did this with the logistic regression, we had a decent level of accuracy, but when we did it with the neural network, we wound up seeing quite a nice leap in accuracy. And so instead of just going straight from calls and years to doing a weighted sum and then coming to the churn code, we actually built a neural network where we had 3 different nodes in here, and then we found weights, all of these weights and all of these weights. And so JUMP did that for us, and this shows us that on the training data, it didn't make any mistake, but on the holdout test data, the unseen data, that it was right 80% of the time. Okay, and so once we've trained this network, the network is really nothing more than a bunch of weights that we can put into Excel, just like we did with the regular regression, and then just put in our calls and years, and apply all of these different weights in the right place and come out with a prediction that's very accurate. Okay, so for example, for each of these nodes there are 3 weights. So you can think of it as the calls weight, the years weight, and the weight of the intercept, so called. So here we got calls and years and intercepts. So these 3 weights are for this one. So that arrow and that arrow plus an intercept. And so this is this node right here. The calls weight, the years weight, the intercept weight, and so on and so forth. Okay, so the neural network then is just kind of a multi-step regression, which means that in order to train this thing, we have to come up with a whole bunch of weights. Okay, so this is a fairly simple one. We've got an input layer, a hidden layer, and then one output layer. We can also, we can extend this so that it gets, pretty complicated. So in this case, we've got 1, 2, 3, 4, 5, 6, 7. We might have 7 inputs. So again, over here, we only had 2 because we had 2 variables. We've got 7 inputs. And now, instead of just having 1 output, we have 12 different outputs. And so now what we have to do is, if we're going to build in, 2 hidden layers of different sizes, now we've got just hundreds of weights. So this turns out to be, very nicely, a setup like this turns out to give you a nice boost in accuracy when you're trying to predict these, these outcomes. Maybe these are, 12 different classes, and each one is a probability that this example is in that class. Let's say 12 different genres of writings. What made this possible, as I said last time, were improvements in software algorithms, particularly backpropagation, which you read about in your readings. And then, of course, the use of graphics processing units, which are really, really fast. They're optimized for these kind of linear algebra operations. So what I would like to do today is to build something that is similar to this. I'm going to show you, I'm going to make a neural network that's going to have input of 784, I think, in the input layer. This layer is going to have 512, I believe. And then we're going to have, let's see, I think it goes, then it goes down to 16. And then finally down to an output of 10. And the neural network is going to be used for a version of this task of image classification. Okay, so as I said, neural networks, one of the real nice powerful uses of those is in the image classification task, where we have some kind of image and we can give it labeled data, and it would, under machine learning, the computer would learn how to identify certain pixel patterns with the label of cat. And so we said before that this has uses in, surveillance and object recognition for autonomous vehicles and so on and so forth. But of course, this is kind of difficult, and I'm not sure what kind of accuracies people are getting right now. I'm going to take on a simpler version of this task right now, which uses the so-called MNIST data set. And I'll show you what this looks like. Okay. Okay. So the MNIST data set consists of 60,000 images of handwritten numbers. Okay, they created, so it's the National Institute of Standards. They created this data set so that people who come up with algorithms for classifying these images can compare how they do with one standard set. So this is kind of like the the real this is what everyone uses to test the accuracy of their computer vision algorithms. So for each digit we have well, this is the testing set, but in the training set we've got 0 through 9, and for each one of them we have just thousands of handwritten examples. Okay, So you can see there's a lot of variety in how people write these, which is what makes it so challenging. If there was, if they wrote them all the same way, it would be a fairly easy problem. But so to account for this variety, differentiate between a 4 and a 7, it's, we need to use machine learning. Okay, so one way you might go about this task, and this was the one that I tried first, was to just well, let me show you what these images look like. Let's go into 3, and we'll just grab one of them, and we'll open it with Illustrator, and then I'll show you what these images are. At the file level, is they are they're really just 28 pixels by 28 pixels, and then each pixel is a shade. Each pixel is a shade of black. So, in this particular example, so this is a 3, and there are, there's 28 pixels going this way, 28 pixels going this way. You can see the width and height dimensions over here. So what we have here is, a 28 by 28, just a matrix, and each one of these things has a number associated with it, everywhere from 0, meaning pure black, to 255, like maybe this one, meaning pure white. So, and then everything in between is a shade of gray. Okay, so we have a 28 by 28 matrix of numbers, or what you could do is just say, well, each one of these is really just 28 times 28, which is 784. It could just say, I'm going to make this, each image is going to be a row of 784 numbers. Okay, so this is what I did. Just for fun, I wanted to see what this would look like and how it would work. So I looped through all the images, all 60,000 of these images, and I just opened up the files, and I extracted all the numbers, and I created a this might take a while to load. So I just created a data set that you might start with. So it would be 784 columns plus the label column and 60,000 rows. So I created this data set. We're just going to look at it in Excel for a second just to get a sense of what we're looking at. Okay, so I put in this column the target, that is the actual digit that it is, and then I have these all these columns from 1 to 784. So that's pixel 1, so upper left corner, pixel 2, and just went through the whole thing. So just row by row all the way down to the lower right corner. And so each of these rows is an image, and you see the vast majority of them are zeros, okay, because we have a black background, and it's not until we get way out here that we actually start to see some non-zeros. Okay, so so now we've got our data set. So now you might just say, okay, well, let's just do a regression. Let's try to predict this number from these 784 variables. I tried this, and it broke jump, it broke R. It was never able to work very well. So that approach didn't actually work very well. But let's go with something a little bit different. So I'm here in Python now, and so what I'm going to do is show you, the next step. Okay, so we weren't able to just unroll the data and try a flat out regression. So let's pull this data into Python and then use some of the out-of-box classification algorithms that come with Python. And then in the end, I'm going to show you a neural network using a library called Keras, Keras, that kind of is a wrapper around TensorFlow. So it kind of simplifies the creation of neural networks. So I'm gonna, the basic pattern here is I'm gonna pull in all of those test images, and I'm going to try a couple of simple algorithms, see how well they work. Then I'm going to try the neural network and see how well that predicts. Okay, so I won't go through all these lines here, but just really quickly, this Keras library makes it very simple to load the MNIST data. So this line here gives you, a list of training images along with those labels, and the labels are just the digits that they are. The images are those 28 by 28 matrices. Okay, so that so it's this 28 by 28 matrix where each value is anywhere from 0 to 255. Okay, so it gives you the training images and the training labels, and then the testing images and the testing labels. Okay, when you load those. So this line right here does basically what my, it converts the data so that it looks like this. So it unrolls it so that instead of having 2 dimensions, it just has 1 long dimension. And you see this is, so it says, okay, now change it so that it's 60,000 rows and then 784 columns. Okay, and it does that. So just to make it nicer to work with, we, instead of having the numbers going from 0 to 255, if we divide them by 255, the numbers are now between 0 and 1. That just makes it easier to work with and feed it into the neural network. So we do the same thing with the testing images too. Okay, and this is, I'll explain what these are later. So the first thing we're going to try, once we load the testing, we load the training images, we're going to go ahead and do an out-of-the-box multinomial NB, which is a naive Bayes classifier. So for each of these different classifiers, what you can, using the sklearn library, you can feed the training images and the training labels into them and just call this fit. So this learns how to classify them. Then you can predict the test images, okay, and then I'm going to print out how well each of those classifiers did on the task. Okay, I won't do all of them, but I'll just show you some of them. So we're going to start off with the simple one, okay, a multinomial naive Bayes classifier. Okay, so I'll run this, and then it will predict how well it does at predicting those images. Okay, so I'll just go ahead and run this. Okay, so not too bad. So what we have here are these metrics that I discussed before, precision recall and F1, and then this shows you how good of a job it did for each of those digits. So it appears as though I like to look at the F1 column, and it seems that the easiest one is the 0. It seems to be really good at predicting the 0, and the hardest one is the 8. Okay, it has a hard time getting 8. In fact, its precision was only 66%. Okay, so overall, we see that it looks like it's about 84%. We can say this is like 84% accurate. Okay, and so that's this would be like those devices that they used to have were used to write, and it was only right 80% of the time. So that's about where we were with that one. Okay, so I'm going to change the classifier now. So now the classifier is going to be something called a stochastic gradient descent classifier. So let's see how well this one does. Okay, so it's going to do the same thing. Train on the training images and the training labels, and then it's going to call the same functions down here to print out the classification metrics. Okay, so now this is better. So once again, let's see. this one has trouble with the 5s. It seems like that's the hardest one. And it seems to do best at the 1. It's good at finding the 1. So for whatever reason, with the pixel data, it works a little bit differently. But overall, now we have a 92% accuracy. So that's an improvement. Okay, so let's instead of doing it this way with a classifier then, and there are more in there if you want to play with this. I'm going to make this code available. It's called MNIST NN classify. So let's just come down here. I'm going to make a neural network with 2 layers. Okay, so there's going to be a hidden layer with 512 nodes. Okay, so picture here. So in this case, I'm going to have 10 different inputs. Okay, or no, sorry. It's going to be 784 different inputs. So each pixel of the image is going to be one of these inputs. So 784. So, and then I'm on this layer, on this hidden layer, I'm going to have 512 hidden units. And then on the output layer, there's going to be 10, where each one of these, so that's the 0, that's the 1, that's the 2, it's going to be a probability that it's that layer. So then I just have to find these weights and then feed the new data in and then see, predict, find the one with the highest probability and say, okay, well, that's what it's predicting. And then I can compare that when I'm testing how well it does with the test data. So that's what we're going to do with these, and we're going to do it in just a few lines. So with Keras, to create a new neural network, we can just call this, we're going to make a sequential network, and then we're just going to add a layer. Okay, so the first layer I'm going to add is going to be 512. Don't ask me why 512, just, try it. And don't worry about this. This is just the function that you're applying at the node, but so this is saying, okay, the input shape. So the input shape is going to be 28 by 28. So again, so it's expecting, this layer is expecting an input of 784 nodes. And it's going to be 1 for each pixel. Okay, so now I'm going to add another layer, okay, which is going to be 10. Okay, and now this activation function, this function converts the output into a probability distribution, so that it does that, has that desired characteristic where these all add up to 1, and the highest probability, the highest one is going to be the most likely digit. Okay, so now that I've added the layers, I'm going to just this code compiles the layer, and it sets some more, it sets some more parameters. Don't worry about those right now. But so now notice that over here, when I made these classifiers, I called classifier fit and then passed in the training data. It's the same thing now. Except now we're fitting the network. Once again, passing in the training images and the training labels, and now I'm going to find out, the accuracy. Rather than getting precision recall for each one, I'm just going to find out the overall accuracy of the network itself. Okay, so now we're going to run this. Okay, so now we get to see it step by step as it's tinkering with all the weights on that network, increasing some, decreasing others, and just trying to optimize the accuracy of its predictions. And so at the end of all this, okay, so now we see when it finally decided it was done, on the training data, it had become 98.8% accurate. Okay, so on the testing data, so the unseen images, it ran the neural network on those and wound up with a 97.8% accuracy, or 97.9%. Okay, so 97% accuracy on unseen data. You can contrast this to the lower ones that we had before. I think we had 84% on naive Bayes, 91%. Now we're already up to 98% with the neural network. Okay, so that makes a big difference. So now we're at a level of accuracy where we can actually reliably identify what what digits are written down. Okay, so there's it can be commercial now, and it can actually be used in high stakes situations. Okay, and it's just because these neural networks. Now, why is it that having this hidden layer boosted the accuracy so much? Well, I don't really know, but I know that when you put it in there, it does. Okay. All right. So the important point to get out of this was just that so neural networks, which because of their the use of the word neural, I think um, these kind of have a spooky association with people's biological process of thinking. But I wanted to emphasize to you that it really is just it's machine learning. We're starting with data, and we're just trying to find out how to combine the data to make a prediction that's accurate. And it just so happens that when we wire these things together in a way that looks like a brain, and then we find all those weights, that it really does wind up becoming more accurate than the methods that we used before.